And in particular, we started warming up to the idea of the problem of finding minimum spanning trees. That's sort of somehow the mother of all weighted graph problems. And it's to recognize what we're trying to compute here. Okay, we said that a tree, okay, we know is a connected graph without cycles. A spanning tree of a graph is a subgraph. What do I mean by a subgraph? It means a subgraph of a graph is a subset of the edges and vertices. Okay, so if here, let's say we have the graph was the social network of the world, the people graph, the friendship graph. Maybe a subgraph of it might be we just take all the people who are nice people and all the pairs of nice people who are really good friends. That would be a subset of the vertices, okay, because not everybody's nice, and a subset of the edges, because not every friendship is really strong friendship. Does everybody see that? In particular, a spanning tree is a subgraph which has the same set of vertices as the original, okay, and the edges form a tree, okay? Any question about it? The minimum spanning tree on a graph, okay, we assume we're given a weighted graph, okay, is the spanning tree with the property that the weight of the edges is minimum, okay? So we're going to sum up each edge has a weight. We're going to try to find what is the minimum, the tree whose total weight, the sum of the edge weights, is minimum. Any questions about that? So let's look at an example here. Here on the left, I've got a picture of some points. Let's imagine that we have the graph, the complete graph, where the vertices are these points in the plane, and the edges represent the the edges represent the the weight of the edges is the Euclidean distance between the 2 points. Okay? If you look at it, B and C over here are 2 different spanning trees. Which one of these should have minimum weight? Which one has smaller weight? Okay? We think about it as an edge-weighted spanning tree. B is, if you look at it, it's got the same vertices as A. The edges form a tree. C has the same edges as the same vertices as A, and forms a tree. The edges form a tree. So B and C happen to be spanning trees. Does everybody agree with that? The minimum spanning tree is the one whose edge weights, the sum of the weights of the edges, in this case the length of them, okay, is minimized. Which one of these looks like the minimum spanning tree? B or C? How many people say B? How many people say C? Okay, no one anymore. Okay, so yes, B looks to me like it's the one that is has smaller edge weights. Okay, does everybody see that? Smaller edge weights means shorter edges, right? It looks like as we go around the C here, we get a lot of about edges that are about as short as possible using that data set, right? And although there is one large edge connecting the center point to somebody, it's clearly there's nobody it can be connected to that's less. Okay? Any questions about it? So this one over here is the minimum spanning tree. The other one is something that we'll talk about, not this class, but later. It's actually the shortest path spanning tree. If you were starting at this central vertex, okay, and you wanted some way to describe the shortest path to get to everybody else, in fact, this path is going to be as the crow flies. Does everybody agree with it? That if we have a complete graph where every vertex is connected to everybody else, and the distance is going to be the distance of the actual edge, the shortest path from here to everybody else is going to be an as the crow flies distance. Does everybody agree with that? So this, in fact, describes the shortest path from here to everybody else. it is also going to make a spanning tree, in this case a star. Any questions about that? About what the spanning trees are, why these are spanning trees, why one is the minimum spanning tree and the other one isn't? Any questions? Okay. The bunk. So, why do we study the minimum spanning tree problem? Every once in a while, again, I've been teaching now at Stony Brook for almost 20 years, okay? And every once in a while, I'm wandering around. Someone comes up to me, and they took my class many years ago. And this happened to me once. Oh, Skiena, I took your algorithms class. Yeah, it was great, man. I still remember Prim's algorithm, Kruskal's algorithm. And I said, okay, what did those algorithms compute? You know the names of them, okay? Why were you actually doing with those algorithms? And they looked at me, I don't know, how would I know, okay? And they walked away and they never made a donation to the university again, okay? But what's the point of this, okay? Prim's and Kruskal's algorithm, which I hope we're going to talk about today, somehow the names are memorable. The names are a guy named Prim and a guy named Kruskal, okay? But they compute this thing called a minimum spanning tree. Now, why do we care about minimum spanning trees? If you can't figure out, remember why we care about minimum spanning trees, the properties of the algorithm are meaningless, okay? So there are a few reasons why every algorithms class talks about minimum spanning trees. The one that's maybe interesting to me but not interesting to you is that it's got a long history. People have thought minimum spanning trees were interesting well before they were really computers, okay? Pedagogically, the main reason why we talk about minimum spanning tree is that it's going to be an example where the greedy algorithm, okay, gives the right answer. What is the greedy algorithm? You may remember when first day of class, I gave you this problem that was the traveling salesman problem. Remember, you had to find the shortest tour visiting all the points. And I asked you guys for an algorithm. And you said, yeah, start here and always go to the closest place. And that didn't work for traveling salesmen. Something like that works for minimum spanning tree. In fact, that we will show that there are a couple of different greedy algorithms where you always make the best local decision you can. And it happens to give you the best outcome overall. Okay? So it's a good representation of sometimes that greedy is good and how we would prove the correctness of such an algorithm. So that's one reason why we're going to talk about minimum spanning tree. Another pedagogical reason is that although the algorithms for finding minimum spanning tree are on a conceptual level very, very easy. In fact, I've even heard people say you should teach them to elementary school children, because somehow it shows them the computers are important and blah, blah, blah. Okay? To make them run fast requires some clever data structures. Okay? And so we're going to look at it as being, there's going to be two dimensions to understanding minimum spanning tree algorithms. One, why is it that it gives you the correct answer? Why is it that it finds the minimum spanning tree? And the other is, how do we make it run as fast as we can make it run? Okay? And that's a data structures issue. Any questions about that? Those are the pedagogical issues of why we talk about minimum spanning tree algorithms. But the other thing is that, that minimum spanning trees are, in fact, useful things. Okay? There are certain applications where it becomes important to try to identify, to compute things that are like minimum spanning trees or like minimum spanning trees. So one of them came to be the following. Suppose, let's say you were, again, you guys are young people. In the beginning of time, there were houses in your neighborhood, okay? And then they invented something called cable television, okay? And these houses had to be wired together to get you cable, okay? So the cable company was faced with the following problem, okay? You have a bunch of houses you want to send a cable television signal to, okay? You can build, here's your, the cable television broadcasting plant. You can connect one of the houses to that. Somehow you've got to create wires between all these houses So they are connected to the main cable central. Does everybody see that? Here is where the cable television signal originates from. Here are the people who in principle are willing to pay for cable, okay, or might be eventually willing to pay for cable. Okay? You want to wire the neighborhood up so everyone can get cable. What is the cheapest way to do it? One way we could do it is, of course, to connect everybody up to the place like this. Does this look like a good idea? Well, it's good if you're being paid by the foot, right? Because it's clear that this is going to involve creating a lot of long wires. Does everybody agree with that? What is the connection that we need in order to propagate this cable signal, okay, as cheaply as possible? What is it? Minimum spanning tree. Does everybody agree with that? Just like I did on the previous slide, we're going to have as input, you're going to take these points, okay, and there's going to be a distance defined between them, okay, where the distance is going to reflect, let's say, the cost of connecting this house to another house, okay. It could be Euclidean distance if you want to minimize wires. But might the cost of connecting two houses be different? Be different than proportional to their distance? Why might it be expensive to connect two houses that are, that are close to each other? Anyone imagine? Yeah? Okay, so one possibility is there's a brick wall. I don't know what you need, a brick wall or something like that. Or you could imagine there's a mountain. Okay, that might be the case, that these guys live on a hill and these guys live on a hill. Okay, it might be more expensive to actually go up or down the hill than anything else. Or it might be that this is a politically connected individual's lawn, and you don't want to, if you're a cable company, you don't want to ruin that guy's lawn to install the cable. Does everybody agree with that? You pay a cost for that. So in general, we are given as input a problem where we've got points representing houses, or vertices representing houses. There is a cost between pairs of houses, representing how much would it cost to run a wire from here to there. Okay? And the question is, how do we use the smallest amount of wire in doing it? And that is minimum spanning tree, or the cheapest cost solution. Any question about that? So the phone companies, the telecommunication companies, the electrical companies have to solve these kind of problems all the time. Any questions about that? So that is one case where minimum spanning tree comes in. Another one that comes in is in clustering. Okay? A problem in a lot of data analysis is that of trying to build clusters. Okay? So what would be an example of this? Again, suppose, let's say I was given the friendship graph of this world, right? Where maybe we were given every vertex was a person, and there were edges that reflected how close were these people, okay? So the two people who weren't very friendly, there was a big, heavy edge between them, right? And people who were very friendly had a low cost. Let's say there was, that friends would have short edges between them, or cheap edges between them, okay? And people who didn't know each other or didn't like each other would have heavy edges between them. So it's not really a friendship graph, maybe it's a hatred graph. The weight is reflecting hatred. Two friends who are really close, they have a hatred of 0. Okay? Two people who really hate each other have infinite hatred. Okay? And you might want to then break this graph into communities. What would, let's say, clusters or subgroups of the graph represent in the friendship graph? Okay? Is there some notion of there being sort of groups or clusters of people in the friendship graph? Well, cliques or cliques in high school, or groups of friends, right? Somehow we have the idea that there is probably somewhere a notion of Stony Brook, where there's a community of people, okay? And within Stony Brook, there is probably a notion of CS majors, okay? And within CS majors, there's probably a few social groups. I don't know how you guys deal with it, but there's probably a few groups of people here, who hang out together, right? So there is sort of the structure of friendship, okay, of closeness, of natural clusters that happen in a friendship graph, right? How might you figure out what those natural clusters are? Okay? Any ideas how we might figure out who the groups of people are, okay, in our friendship graph? Okay? Well, we have minimum spanning trees. What would the minimum spanning tree of the friendship graph look like if we had the minimum spanning tree of a graph where people were close had small edges, and people who didn't like each other or didn't know each other had heavy edges? What would we think the minimum spanning tree would look like? Okay? What it would be is, let's come back here. I claim what it would be is that you and your friends, there's going to be nice short edges between them, right? And then, though, to collect your group of, I don't know, let's say we've got the Crips and the Bloods in here. I don't know, well, okay, just to make it up. There's going to be somehow, probably, some link between a Crip and a Blood, but it's probably going to be further away. Does everybody agree with that? That's going to represent the long edge. Does everybody agree with that? If we kept merging things up, eventually there would be a connection. Here are the English majors. They are busy forming their own sub-spanning tree. There's going to be an even longer edge connecting the computer science together, the computer scientists to the English majors, than the Crips and the Bloods, let's say. Okay? I don't know about that. Okay, don't take this too literally. Okay? But you could kind of imagine that as you link communities further away, you're going to need a heavier edge to do it. Isn't that right? So how might you find what the natural communities are? One possibility is you take the minimum spanning tree and you delete the heavy edges. Okay? How do you define what a heavy edge is? Well, it depends what you consider to be something belonging to a different community. And does everybody agree that if you take the minimum spanning tree and you delete the large edges, you're going to have smaller connected components of people? Those are presumably representing clusters or communities in some way. Does that make some sense? Okay, any questions about that? Okay. So these are the kinds of reasons why minimum spanning trees are important. Okay, any questions? Okay, so algorithmically, there's a bunch of things you do with minimum spanning trees that are interesting. One of the war stories in the book describes where I actually had to find a minimum spanning tree, sort of to do clustering. Okay, there was a company that contacted me. They have a printed circuit board tester. Okay, and it was this robot that moved around, bzz, 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 okay, but it had two testing arms and it was pretty complicated. And they wanted to break up their, their set of points into somehow sets of overlapping clusters. Okay, well, you see what happened? I took as input these set of points, and I had to construct overlapping clusters. Okay, where within a cluster they were close, but all the clusters were somehow connected. So what did I ultimately do? Basically, I found the minimum spanning tree. The minimum spanning tree was going to be connected, right? And then basically I deleted the large edges. The large edges formed their own clusters. Okay? And they served as bridges between other clusters. Okay? Any questions about it? So minimum spanning trees naturally arise in these kinds of problems. Any questions about that? Okay? Does everybody see why minimum spanning tree can be your friend? Any questions here? Okay. So the question is actually, let's think about it now. How would you find a minimum spanning tree? Let's actually start by thinking about this problem from scratch before we get into how I do it, just to warm you up. Here as input, you've got a weighted graph. Okay, it doesn't have to be a geometric graph. It can be a graph with arbitrarily weighted edges and vertices. And we want to find the lowest cost tree, okay? The one whose tree whose edges sum up to have the smallest sum of weights. How can we do it? Let's think about this. How would you find such a tree? Okay, say you. You're saying start from one node and go to another node to find the one of shortest weight. And then what are you going to do? Find the one with next node of shortest weight, right? And then keep doing this, right? So he's going to go ka-chunk, 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 ka-chunk. Is he going to find the minimum spanning tree? Who here says yes? Who here says no? Okay, the no's have it. What would be an example of a minimum spanning tree where he's not going to find it? His tree, notice, is a path, right? A path is a tree. There's no cycles in it. But if he's always going from one point and walking ka-chunk, 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 he's got a very skinny tree. What if, let's say, my points were a point and the points were, let's say it was a star where I had a hexagon here, right? A snowflake-like thing. What would the smallest weight tree be? I'll tell you it will be the snowflake. Okay? If the points are, close enough. Certainly, that may not be convincing. But certainly if I have 3 of them here, I think it is pretty clear that this is going to be the minimum spanning tree, and not something that's going to look like this, which is the alternative. Does everybody agree that my black one is shorter than your my blue one is short? That my black one is shorter than your blue one. Any questions? Okay. So although the minimum spanning tree algorithm is simple, you'll see it when you see it. It's going to look simple. Let's respect it. It wasn't that simple. Okay. Any questions? Any other ideas how we can find the minimum spanning tree? Okay. So you're saying that instead what the mistake was I started here. You want to start here just like him. Go to the shortest neighbor. But in general, you don't want to, now for your next choice, you want to link somebody else into the tree. But it doesn't have to be the last point. It can be one of the points we have gone to. Everybody see that? So he's saying, well, what's the next closest one? Well, I can get to this point. From here, I'll do that. Now, to link to my next point, what's the shortest? Each point what you want to do is find what is the shortest distance between a point that is in the club and a point that is outside the club. Does everybody see that? Not just the last member of the club, but anybody from the club is allowed to be a candidate. Right? So yeah, maybe I'll link this guy in. Okay? Now that these guys are in the club, who's closest next? Well, it looks like it's that guy. Okay? Any questions about that? Do people see what this algorithm is and what the difference is? Is this algorithm correct? I see a lot of people nodding. How do you know it's correct? Okay. How do you know it's correct? Okay, well, we need to prove it. That's sort of the point. I will tell you it is correct. But this is not obvious now. But maybe let's go through with this one. Why is it correct? I'll tell you it's correct. Now convince me. Okay? Why is it correct? You could say, well, Skiena says it's correct. But okay, but is there an argument why it's right? Yeah, you. You're starting with the points of shortest weight first. That may be true, but it's not going to be why that's different than his algorithm. He was somehow saying something about starting with the shortest points, okay? So we need something a little more precise than that. Yeah. Okay, you're giving me a belief thing. You're not really, again, it's not fair for me to ask you for a proof from your heads, okay? But you're not giving me yet a rigorous conviction. You're talking your way through it, right? You're saying it can't go wrong. That's why it's right. Okay? That's basically what I'm hearing. Okay? Any questions about that? Yes, you. Well, you're saying it's getting better. You're saying the reason why it's right is because it's always getting better. Well, what is getting better? The tree is always getting a new member to it. But this tree could also be getting a new member to it each time, right? So what is getting better each time? Well, every time you're adding another point, your minimum spanning tree so far is getting longer, isn't it? So, in some sense, things are getting... I don't see it... Oh, yeah. Yeah, yeah. So what you're sort of saying something about, you may be trying to say, I'm not sure if I believe this is what you're saying, but you may be trying to give an inductive kind of an argument. You may be trying to say that when I start building it, okay, it's on a subset of things. Suppose that so far I have the minimum spanning tree overall. I'm going to add the closest point to it. Couldn't have done anything better than it, right? Therefore, this has to be the best one overall. And the short answer to that is not obvious to me, okay? Why might that not be, again, why is that not yet completely convincing to me? You're sort of saying that the best one on these people so far, when you add another guy to the mix, that it's not going to make the overall solution with the other guys change. So let's look at something like this. Let's say that I had a point here and a point here and a point here and here. And I say I want the minimum spanning tree is this. I'm now going to add another point to the mix. I find the shortest minimum spanning tree is going to edge like that. This must be the minimum spanning tree of the three of them. That's what you're sort of saying, right? You're sort of saying, it sounds to me, look, Ma, I got a minimum spanning tree of these 2 points. Okay? It's the best you can do on those points. I'm adding another point to the collection, right? And I'm connecting it the best way I possibly can. Doesn't this have to be globally optimal? And the short answer is it doesn't, right? Isn't that the right minimum spanning tree for these points? Does everybody see that? That the 2 blue edges are really shorter than the 2 red edges. Okay? Any questions about that? So we should respect what we're going to see here. Okay? I mean, the algorithm is now right, and you figured it out the second time around, and that's good. Okay? The thing is, to prove that it's really going to give us the correct answer, there is some subtlety here. Does everybody see that? Okay? Question? Well, you're saying that, look, it doesn't look like I'm doubling back. Yeah. Okay, I'm not sure I know what you're saying, but I'll argue that it doesn't matter what you're saying for the following reason. Okay? This is a problem that is on graphs. Okay? Does everybody agree that fundamentally this is a problem on weighted graphs? Is there a notion of left and right and zig and zag on weighted graphs? There might be on graphs laid out in the plane. Okay? But so somehow that if you're trying to capture something from this geometric instance, in fact, the algorithm that we outlined will work on any weighted graph. Okay? And it doesn't require the weights sit in the plane like that. Does that answer your question? Were you satisfied with that? Okay, thanks. Yeah, thank you for the question. I didn't mean to be dismissive of it. Okay? Any questions here? Okay? So let's think what actually there is on minimum spanning tree. Okay? Now we should start to respect it a little bit. Okay? So the algorithm that we developed here is called Prim's algorithm. Okay? Who invented it? Prim. Okay? So what is Prim's algorithm? Okay? It starts from one vertex and grows the rest of the tree an edge at a time. As a greedy algorithm, it is going to pick the cheapest edge, which grows the tree by one vertex without creating a cycle. Okay? That's the condition that we had before. Does everybody agree with that? We constantly want to grow it. We want to add edges, but we want it to stay connected. Okay? And do that. So again, this is a pseudocode version of the same idea. Start from an arbitrary vertex. While there is a non-tree vertex, meaning not everybody's in the tree, select the minimum edge of minimum weight between the tree vertex and a non-tree vertex. We say that a vertex is in the fringe if it is not in the tree, but it is connected to an edge that is to a vertex that is in the tree. Right? Does everybody think about what this Prim's algorithm is doing? It's going to be growing a tree, right? From some starting point. Initially, some vertices may be so far away. Excuse me. Some vertices may be so far away in terms of the number of edges of the shortest path to that. It won't be that there's any chance of adding this vertex until we have added one of its neighbors. Does everybody agree with that? A vertex has no chance of getting into the minimum spanning tree until one of the guys who's adjacent to it is. Right? Because we'll always be growing a connected tree. So we say that a vertex is in the fringe, basically, if it is connected to somebody who's in the tree. It is unseen if it isn't, if it's more than one edge away. Okay, there's no hope to add it now. Any questions about it? So what is Prim's algorithm in action? Let's take a look at it one last time. We start out from edge. Which is the first edge that we're going to be adding here? The one of weight 5. Okay? Now, which is the next edge that we're going to be adding? We're going to add a weight of 7. Which one should we add? This one or this one? Turns out it doesn't matter. Okay? Because right now, recognize if we haven't specified how we're going to break ties, right? So if Prim's algorithm is going to be correct, it better be correct regardless of how you break the tie. Does everybody agree with that? So I happen to have chosen this one. Now, which is the next vertex, edge weight that we're going to pick? The edge of weight 3. Why? Because that's the nearest way to get in the fringe, right? This, and this is in the fringe. The cheapest way to get there is at cost of 3. We will do that. Now, which is the next edge that we're going to add? 2. Which one should we add? Doesn't really matter, right? Because they're both 2. I happen to have added this one. Now, which one do we add? We can add this one now, right? That's the other one in the fringe. Okay? What is the next step to add? 4, because we have to link the last vertex into the tree. Does everybody agree with that? Any questions? Okay? What was the weight of that tree, just to make sure we understand it? 5, 7, 3. Okay, 4, 2, and 2. Does everybody agree with that? Notice we could have done it a different way. What if we had taken the different route? We started out taking that edge. Suppose we had picked this one. Now what is the cheapest thing in the fringe? Does everybody agree that it's now that edge? And now what's the cheapest thing in the fringe? 2. And now what's the cheapest thing in the fringe? 3. And now what's the cheapest thing? So what's the cost of this thing? This thing is 5, 7, 2, 2, 3, 4. Does everybody agree with it? It happens to be the exact same weight as the other one. Any questions? So there might be multiple trees with the same weight. But if Prim's algorithm is going to be correct, it's going to have to find a minimum weight tree, okay, on any graph. Questions about how the algorithm works. Okay, that should be clear. The question is, why is Prim's algorithm correct? Why does it have to guarantee us the minimum spanning tree? It's a rhetorical question for those of you with hands up. Okay? Okay? Why does it give us the correct answer? We're going to use a proof by contradiction. What is the idea of proof by contradiction? The idea is I'm going to assume that the opposite is true and then go through the consequences of that decision and prove that it was wrong, that my assumption, okay, was wrong. If my assumption that the algorithm didn't work was wrong, it must mean that the algorithm does work. Does everybody agree with that? That's the idea of proof by contradiction. So suppose Prim's algorithm is wrong. What does that mean? That means there has to be a graph here. Somewhere in the world there is a weighted graph and a starting vertex where Prim's algorithm gives the wrong answer. Does everybody agree with that? If Prim's algorithm is wrong and there is no answer, I mean, that means it has to not always give us the right answer. So there must be some example where it is wrong. Does everybody agree with that? So let's say Prim's algorithm is wrong, and here is the example where it is wrong. Okay? Further, we saw that there can be multiple spanning trees. Does everybody agree with that? Multiple minimum spanning trees? If Prim's algorithm is wrong, there is going to be a point where it adds an edge to the spanning tree, such that there is no hope for a minimum spanning tree, using all the edges we have so far. Okay? So let's think about this example where we're wrong. Say, okay, Prim, do your thing. Okay, I add this edge, I add that edge, I add this edge. The claim would be that if Prim's algorithm was wrong, there is some point at which adding this edge was the fatal mistake. Does everybody agree with that? If it was wrong, it meant that at some point we added an edge such that there is no minimum spanning tree containing these edges that we had. Do people agree with that? That's what it means to be wrong. Okay? So let's think about it now. Suppose we are wrong. What does that mean? That means that we were right up until the point where we added this edge. That means, what does there have to be? There has to be some minimum spanning tree. Okay? There has to be a minimum spanning tree. One that is, by definition, cheaper than what we found. Because remember, we were finding, for you said we were wrong, right? If I took your spanning tree and add back this edge, the poisoned edge that I added, what happens? Okay? Prim's algorithm was wrong, supposedly, right? This was the edge that did it. What if I take that edge back and add it to your minimum spanning tree? What will happen now? I will create a cycle. Does everybody see that? In any minimum spanning tree, in any spanning tree, you add any edge, ka-chunk, you have a cycle. Does everybody agree with that? Well, what is the problem here? There was a fringe. If we took a look at this so far, at the time I added this thing, okay, you, okay, somehow there is an alternate path now to the edge that I added, right? There was the edge that poisoned us went from something that was in the tree to something that was in the fringe. Does everybody agree with that? The minimum spanning tree that supposedly is right, okay, had to have had an edge from the fringe. If we take a look at that cycle, there was a cycle that is created by adding our edge back to the spanning tree. What do we know about the weight of this edge? See this edge over here? What do we know about the weight of that edge? This edge here, let's say this was vertex X, this is vertex Y, this is Z. What do we know about the cost of weight of edge Y, XY, relative to the cost of XZ? XY has to be less than XZ. Why is that? Why do we? Because I was picking the cheapest guy from the fringe outside the fringe, right? I had the opportunity to pick edge XY, and I passed it off. What did I pick? I said, I took the cheapest edge that I could. I looked edge XZ in the eye, and I turned my nose up at it, right? Because this was less. So we know edge XY is less than that. So what do I now know? Suppose I take your tree and I delete edge XZ from it and insert edge XY. Is it still going to be a spanning tree? Let's think about it. If I have a spanning tree and a cycle, note that I can blow away any single edge on the graph, any single edge on that cycle, and I'm going to be left with a spanning tree. Does everybody agree with that? If I have a cycle and I delete any single edge, this thing still be in one piece, right? If I take a cycle and I delete an edge that costs $100 and replace it with an edge that costs $99, did the weight of my tree go up or down? Down, right? Now you told me my algorithm was wrong. Prim's algorithm was wrong, and that you gave me the minimum spanning tree, right? Well, how could you have given me the minimum spanning tree when I just show you a cheaper one? Everybody see that? What you told me was the minimum spanning tree couldn't possibly be right. Because if it was right, I have just shown you a cheaper minimum spanning tree. Does everybody see that? So you were wrong when you told me Prim's algorithm was incorrect. And if you're wrong that Prim's algorithm was incorrect, then what happens? Prim's algorithm is correct. Any questions about that? How many people sort of see it? How many people don't see it and want to see it? Okay? See a couple of hands. Let's just do it one more time. It's kind of important to see why it is right. Okay? The argument is this. Okay, let's go through my text here. Suppose Prim's algorithm was not right. If so, there is something it will fail. And if so, there will be a first edge that Prim's inserts such that we have lost it. Does everybody agree with that? Sort of like you're on some kind of a quiz show or something like that. You need to get all the answers right. And you're giving me the answers one by one. Yes, it's a D. It's an A, it's a C, it's an A. That was where you blew it, right? So if your algorithm is wrong, there is a point at which there is an edge that Prim inserted that couldn't have been there. Meaning that with what we have so far, we couldn't build a minimum spanning tree. Okay, maybe you're right. So I'll take that edge out and say you finish it up and give me a minimum spanning tree. And say, look, here is my minimum spanning tree. That's what I've got here. This is where I went wrong. you'll say, no, this was really the part of the tree that was supposed to be there. Well, when I add my supposedly wrong edge back into your spanning tree, I've got a cycle, right? It has to be a cycle, because adding an edge to any tree creates a cycle. More than that, you had to have had an edge that connected from the fringe to this cycle. Okay, there was sort of something that went, this cycle somehow had to have started in the fringe. It had to have left the fringe. It had to have left my partial tree. That edge where it exited the partial tree was something that Prims didn't have a chance to add yet, but you think should be in the minimum spanning tree. I claim I will still have a spanning tree if I add this and delete that edge. And further, it will have to be a shorter spanning tree, because I added this edge, added edge xy in Prim's algorithm, because it was the cheapest edge from going inside to outside at the time that I was making that decision. I had the option of picking this one and didn't. And the reason I didn't is because this had to be bigger than that. Does everybody agree with that? And so therefore, okay, I can replace it. I get another spanning tree with smaller weight. So you lied to me when you said Prim's algorithm was wrong on this example. Any questions about that? How many people sort of get it? How many people don't get it? Okay. Any questions about it? Okay. Any questions? So the interesting thing is, and try to understand the proof. It's not that horrible if you think about why it is correct. Any questions about it? Okay. Any questions? Contradiction. Okay. Yes. Okay, so what you're complaining about, I think, is that, to be precise, you're complaining about my disproof of your algorithm by saying that I didn't really disprove the algorithm you thought you were proving. And that was actually true. What I believe, though, that what I was doing was the condition that you were stating as to why it was right, okay, was not a strong enough condition. Really what you're saying is, if I have the minimum, a subtree that happened to be built by Prim's algorithm, then I can't go wrong. Okay, but that's really, if you think about it, just stating that is really restating Prim's algorithm, right? Okay, any questions about this idea? Proof by contradiction. Any questions about it? So that is why Prim's algorithm is correct. Okay? And so we can't go wrong with our greedy strategy. We make the globally right decision by making local moves. Any questions about that? Okay, so how much time does Prim's algorithm take? Okay, we're now going to accept it's correct. Being correct is a good thing. Why is Prim's algorithm, how fast is Prim's algorithm? Let's look at the pseudocode and tell me how fast it is. While there are non-tree vertices, how many times will that loop go around? You have n vertices and m edges in the graph. N. Does everybody agree that we're going to make n iterations? In each iteration, we're going to go and find out what is the smallest weight edge between a tree and a fringe. Okay? How can we do that? We have sort of a world where, let's say we have a vector right now, an array. For every vertex, a Boolean array, is vertex I in the tree or not? Does everybody agree with that? Originally, nobody's in the tree except our starting vertex, right? Now we want to go and select the minimum weight vertex between the tree and the fringe. How can we do that? Can we give me a concrete way to do that? to select the minimum weight tree edge between the tree and the fringe. What would we want to do? Yes? Right, 4i goes from, or do a iterate through our adjacency list. For each edge ij, is it true that one of I and j is in the tree and one of them is not, right? And if so, am I the cheapest edge I've seen so far? Does everybody agree with that? That would do it. Okay? So I claim that by doing that, that would run in, this would take order n plus m time, because you've got to bop through the entire adjacency list, right? This algorithm, and then once we do it, what are we going to do? We add the edge we want, and we add the vertex to the tree, changing that bit to be true, right? So this looks like something that is n times n plus m time. We usually think that n is less than m, right? In a connected graph, the number of edges is always greater than the number of vertices. Does everybody agree with, or close to it, right? What's the smallest number of edges in a connected n vertex graph? N minus 1. So n and n minus m is always going to be order n if it's connected. Usually m is bigger than n. So we would say it's order n times m. Any questions about it? Does everybody see? Question, yes. Very good question, okay? I like that question, okay? The question is, why is it that we can select, how can we identify what the minimum weight edge is connecting between a vertex that is in the tree so far and somebody on the outside? Does everybody agree with that? How am I going to do this? Here is my adjacency list. It's got in a matrix a vector of size n, and it's got a total of 2m items in my linked lists, right? I'm going to maintain also a data structure that is another n by 1 array that is going to tell me true or false, is vertex I in the tree so far, right? Initially, I'm going to initialize my start vertexes in the tree, and everybody else is not. When I add another vertex to the tree, it's just a question of flipping that bit. Does everybody agree with that? Now, how will I find out what is the cheapest minimum weight edge between a vertex that is in the tree and not in the tree? What am I going to do? I'm going to bop through this adjacency list. Bop, 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 bop. When I look at this guy, this is the ith list. In this element, this linked list cell, it tells me I is connected to j, and the weight of it is 100. So what am I going to do? Look at I. Is I in the tree or not? False, it's not in the tree. Is j in the tree? False. Well, neither of them are in the tree. This cannot connect us from the tree to the tree, right? It could be that this is true. If one of them is true, one of them is in the tree and one of them isn't. That's what we want, right? If both of them are true, it's connecting two people that are already in the tree. We just create a cycle. It could be they're both false, and that means that these are guys that are not yet eligible to be in my tree, right? But by cruising through, I can pick this. In constant time, I can test the legality of each edge. N plus m is the time that it will take to check every single edge in that adjacency list. Times constant, this is order n plus m. Any questions? How many people see why it is n plus m? Okay, how many people don't see why it's n plus m? Any questions? Okay? So this is a n times m algorithm. Okay? Any questions about that? Okay? And in fact, what I would like to okay, any questions about that? In fact, there is a way to do it faster. There is a way to do it in order n squared. Why is order n squared better than n times m? Well, if it's a sparse graph, they're the same, right? So I don't know that the graph is sparse. If the graph is sparse, the number of edges is linear in the number of vertices. This algorithm is, my implementation is going to be the same as the one I just gave you. If the graph is dense, though, where every edge was, vertex was connected to every other vertex, okay, which is the case, for example, in that geometric instance, right, where we had every pair connected to every other pair, okay, then that would be n times n squared. That would be n cubed. So if I can make it run in n squared time, that is much better than running in n times m. Does everybody agree with that? Any questions? What do we have to do faster? Let's take a look at this. What do we have to do faster in Prim's algorithm in order to make it run in n squared time? Okay? Do we have to reduce the number of iterations of this? Or do we have to speed up the selecting of the minimum edge? We have to speed up this. This is what took order m time, right? Does everybody agree with that? We have to find a way to figure out who is the next most desirable guy to add. Here's my tree. I want to look at all the fringe edges that go from trees, from all the fringe edges that pass from a vertex that is in the tree to somebody outside the tree. Does everybody agree with that? How many edges might there be in the worst case that pass from at some point in the algorithm, okay, between the vertices inside and the vertices outside? Can there be a quadratic number of edges? The answer is yes. What if I have n over 2 vertices inside my tree and n over 2 vertices outside the tree, right? All of these n over 2 vertices are connected to all of those n over 2 vertices if it was a complete graph. Does everybody agree with that? So even if I just knew exactly what edges were in this fringe, it would still potentially take quadratic number of edges. Do people see that? It's not just that I'm looking at edges that are ridiculous, okay? But here's a question for you. If I have a vertex that is in the fringe, which edge is going to be the one that might link me in? Okay? Suppose I'm in the fringe, and I'm going to get to the club. There might be n over 2 edges to me from people that, it might be, here in this case, it could be n over 2 edges from somebody in the fringe to me. Do I need to keep track of all those different ways of getting into the tree? Which is the way that I will get into the tree? By the shortest one. Does everybody agree with that? So how are we going to make this faster? What we are going to do is keep a data structure that is going to be keeping track of, for each vertex, what is the cheapest way I know of so far to get me into the tree? So each vertex, if I have a vertex that's in the tree, I'm already in the tree, right? If I am not in a tree, some vertices will be unseen, and there's no way to get me into the tree, right? So the cost of getting me into the tree would be infinite. But for some vertices that are in the fringe, that are not yet in the tree, there may be many edges that will get me into the tree. All I want to know is what is the cheapest way of getting me into the tree. So I am going to maintain a data structure, okay, that is going to be doing the following. It's going to basically keep track of, I'm going to keep track of, am I in the tree yet? That's what that bool was for. And what is the cost of getting me into the tree? Okay? So what is my algorithm going to be doing? Originally, the cost of getting me into the tree is infinite, because you need an edge to do it, right? In general, the algorithm is really going to look like this. While V is not yet in the tree, okay, put it in the tree. V is the next vertex. V is the starting point, the next guy to come into the tree. What is my algorithm going to do? If I'm not yet in the tree, put me in the tree. Then go through all the edges coming out of me. Under what condition is the edge from this new vertex V to a guy who's not in the tree? Let's call him X. Under what condition is this edge going to be interesting for X? If what? Well, if V is in the tree, and I now look at the outgoing edge from X, out from V to X, if the edge from V to X is cheaper than the cheapest edge I have already seen from someone in the tree to X, then this new edge is going to be interesting to me, right? If before X knew how to get in at the cost of 50, and this edge is of cost 45, now this is a better way to get X into the tree, right? So we're going to look at all the outgoing edges from X and ask ourselves, is the edge going from V to W, okay, is the cost of the distance to the best, is the edge cost of this weight less than the cost of the cheapest way to get in there so far? If it is, we'll update the cost of the cheapest way to get in there so far. Okay? And we'll say, congratulations, the cheapest way to get the W into the tree is our new vertex Y, V. Any questions? So how much time does it take to go through all the outgoing edges from vertex V? How many times will this loop be that goes around all the outgoing edges of vertex V? How many outgoing edges can there be from V? N minus 1, I can't, or N, okay? I like to keep life simple for me, right? It can't be more than N, right? So the cost of updating all these elements that are reachable from V, with whether this is a better way to get into the club, okay, takes linear time, right? Any questions? And now we've put V in the tree. How do we figure out who's the next guy to come into the tree? What is the next vertex to come into the tree? How would we find out what the next vertex is now that we've updated that? What is the next vertex to come into the tree? Okay. What is the condition on Prim's algorithm? Yes. The smallest thing in the distance vector that is not yet in the tree. Does everybody agree with that? So what am I going to do? For all the vertices, if I is not in the tree, and the cost of getting I into the tree is less than the cheapest one we already know of, I is my best candidate for getting into the tree. Does everybody agree with that? How much time does it take to find the minimum of these n values? Order n, right? In fact, if we do it this way, Smart took order n to update the consequences of adding a vertex, and this part took order n to find out who's the next guy that's in the club. N plus n is n. And by using this data structure to keep track of the best edge so far to get us into the tree, In fact, it only takes linear time for update. Any questions about that? How many people sort of see why it's linear? How many people don't see why it's linear and want to see why it's linear? Okay? So look at, this is one I want you to look at in the book and to try to read and understand why it's linear for a couple of reasons. We're going to see this algorithm again in an important disguise in a few classes. Okay? So you're going to have to see it again. You might as well understand it now. Okay? The other thing, it's a good example of what you can do with the right structure. Here, the reason it went from order n times m to order n squared is that we kept track of the right information so we could update it quickly and just keep what we needed. Okay? So seeing the intricacy of why this data structure does what we want for prims is a good thing to do. Any questions about that? Any questions of why prim's algorithm is a good thing? Okay, why it runs now in n squared time and why it has to be correct. Okay? Any questions? Okay. So as we said, if you read the analysis, prim's algorithm takes order n squared time. Okay? And that's the time analysis with the right data structures. Any questions? Okay, good. So, in the worst case, okay, how much time might it take to do minimum spanning tree? Can we ever hope to find the minimum spanning tree without looking at every edge in the graph? Okay? If I have a graph with m edges to it, is it possible that I could find the minimum spanning tree without looking at all the edges? Weir says yes. Weir says no. Okay? I claim there's no hope to find the minimum spanning tree without looking at any edge. Every edge. Why is that? Suppose you didn't look at the minimum the distance between I and j. If there was one edge you didn't look at, suppose the cost of that edge was minus $1 billion. You would probably have regretted that, right? Does everybody agree with that? So I claim that no matter, especially in a world of negative edges, weight edges, no matter what the rest of the edges are on the tree, a bigger bargain may lie on any edge you didn't look at, right? So you'd better, in the course of finding the minimum spanning tree, look at every single edge in the graph. Does everybody agree with that? And how many edges might there be in the graph, in the worst case? How many? N squared. It's supposed to be a thing you've realized by now, right? In the most densest graph, every vertex is connected to every other one. N vertices connected to n others is n squared. Right? If you have to look at every single one of them just to make sure they're not minus $1 billion, it's clear that in the worst case, there is no algorithm that can run fast, always run faster than n squared. Does everybody agree with that? Because if you give me a graph with n squared edges, okay, I'm going to have to look at all of them. How fast did prim's algorithm run? N squared. Does that mean that prim's algorithm is the best of all possible minimum spanning tree algorithms? Okay, probably not, okay? That's the right answer is probably not, okay? It certainly is in the worst case on dense graphs. On dense graphs, you can't hope to do better than it. If you tell me you've got a graph which is a complete graph, find the minimum spanning tree. There is no possible way to beat prims. On the other hand, what if I give you a sparse graph? Is it possible, what if I had an algorithm that ran in n log n plus m? Okay? In the case of dense graphs, what would this be? N squared. In the case of sparse graphs, what would this be? N log n. Does everybody agree that if you can do this, this would seem like a better thing than prims? Does everybody agree with that? Truth is, I don't know how to do that. But what if I gave you an algorithm that ran in m log n plus m? Okay, I guess, would the plus m make any difference? Now, which is better? Prim's algorithm or this magical m log n algorithm? Answer is it depends. Which would be faster on a dense graph where you had n squared edges? Prims. Which would be faster on a sparse graph where you had n edges? This other one, right? That would be n log n now. Does everybody agree with that? So we're going to look at one more minimum spanning tree algorithm, partially because it is a faster one on the main, let's say, pedagogical real reason is that it's going to be faster on sparse graphs. Okay? But again, it gives us more opportunity to think a little bit about what is correct and how you might find minimum spanning trees. Any questions about that? So what is Kruskal's algorithm? Can anybody suggest an alternate approach completely to finding a minimum spanning tree? Remember, we worked out Prim's algorithm right here, where we started from some vertex and built out a tree. Can anybody think of any other kind of an approach to build a spanning tree? Sorting. Sort what? Sort the edges. And if we have the edges sorted from smallest to biggest, what are you now suggesting? You're saying add the smallest edge we can, right? So you're saying, look, 2 is the smallest edge, 2 is the next smallest edge, 3 is the next smallest edge, 4 is the next smallest edge, right? That we can't do now, right? We got a problem. Add the smallest edge that won't create a cycle. Is that right? Now what are we going to be adding here? This. Oh, let's make it blue. Right? Like blue. What's the next smallest edge that won't create a cycle? 7. What about this guy? So the difference here, notice this guy here is of weight 5, right? If we sorted them and inserted them from smallest to biggest, we're no longer growing the minimum spanning tree from starting here and branching out. Now what you're proposing is to percolate instead, okay? And add the lightest weight edge that you can, right? So this would be a minimum spanning tree, okay, by the arguments that we had here. Does everybody see that? We built it up from smallest to biggest by inserting edges not respecting trees, but only making sure they didn't create cycles. Does everybody see that? Any questions about that? So what is the idea with Kruskal's algorithm? Okay. With Kruskal's algorithm, we're going to take all the edges in the graph and sort them by weight. Okay. What are the edges sorted by weight? I see 2s, I see 3s, I see 4s, I see 5s, I see 7s, I see 9s, I see 12s, right? I am now going to add the edges. I see 2 2s. How many 3s? 1 3. How many 4s? 2. How many 5s? 2. How many 7s? 2. How many 9s? 1. 12s? 1. 3 7s, I'll trust you. Okay, 3 7s. Now what am I going to do? I'm going to add these edges in cost from smallest to biggest. Okay? And say, I'll add one of these, and add one of those, and keep adding edges from cheapest to biggest unless they create a cycle, right? I can't have a cycle in my minimum spanning tree, right? So I can't add this edge as again, I'm sorry, I can't resist. I pointed to it on the screen. This edge I can't add. Does everybody see that? If I add it, it will create a cycle. But I have another edge of weight 4 here. And now I've dealt with all of these guys. Where's my edges of weight 5? There's one here, but that doesn't help me. It creates a cycle. This guy does not create a cycle. Okay, so I'm going to add it even though it's not connected to what I have so far. Because if I go through all the edges, I will eventually add everybody. This guy can't do it. This guy can't do it. In fact, now everybody's in, right? So I'm going to keep adding vertices from cheapest edges, from cheapest to most expensive, provided I have not created a cycle. Okay? So instead of starting from a tree and growing out, okay, I'm going to pick something here and here and here and sort of percolate it up. Okay? Any questions? Actually, I have somewhere on my website, I have a website where we built an animation of this algorithm. Actually, I don't want to give you it. I have the author of a package for doing discrete math called Combinatorica. It's not important. Combinatorica.com. Go to combinatorica.com. There I've got an animation of minimum spanning tree of the United States capitals. And you can watch this algorithm work. Here you've got all the cities in the United States. Right? That's sort of what the United States looks like, right? And how does it build the minimum spanning tree of the United States? You start watching it, and nothing looks like it's happening. Why? Because there are a bunch of cities that are really close together, and the edges are so small. But we're going to keep adding edges between the closest pairs of cities we have, such that we don't yet create a cycle. And gradually, at the climax of the film, we start adding big edges. Ka-chunk, 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 ka-chunk. And that is Pruskal's algorithm in action. Any questions about that? So think about why this is right, and we will talk about this next class. Any questions? Thanks for your attention. Some of the regrades from the exams are here if you want to pick them up. Okay, thank you.